Welcome to the deep dive. Ever tried juggling chainsaws while riding a unicycle? That's kind of what concurrent programming can feel like sometimes.
Yeah, it definitely adds a layer of complexity.
Right, making your software do multiple things at once, it just dramatically ups the chances of things going wrong compared to just simple step-by-step code.
Exactly. Concurrency is really all about orchestrating multiple things happening while seemingly at the same time. This could be just an illusion on a single processor, where tasks are switching really fast. That's apparent concurrency.
Okay.
Or it could be actually happening in parallel on a multi-core chip, and that's real concurrency. The tricky part is managing all that without, tripping over yourself.
And to help us navigate this Highwire Act, we're diving into the Ada-style guide concurrency from Wikibooks. Ada is known for being robust, right? So it seems like a good place to look for reliable ways to build these concurrent systems.
Definitely. It has some really solid features built specifically for this.
So our goal today is basically to pull out the key advice from this guide stuff you can actually use if you're building concurrent software or just, curious about how it's done properly. We'll be looking mainly at Ada's core tools, protected objects, and tasks.
Yeah, those are the fundamentals for managing shared data and modeling those simultaneous activities.
Okay, let's unpack this. Protected objects first.
Sounds good. Think of protected objects as the traffic controllers, specifically for data that multiple parts of your program might need to touch. Their main job is mutual exclusion.
Mutual exclusion.
Yeah, making sure only one task gets access at a time. It prevents those nasty race conditions where the result depends entirely on who gets there first, which is, unpredictable. They're also really good for building synchronization tools, like, say, a resource monitor, where only one process can use a shared device.
Gotcha. And the guide jumps right into suggesting we keep these protected objects wrapped up inside packages. Is that just for neatness?
Well, it's mainly about good structure and encapsulation. It's like keeping related tools together. It makes it really clear what code is responsible for managing which piece of shared data safely. It's not just neatness. It's about maintainability.
Makes sense. Keep things organized.
Exactly. Now, here's something interesting the guide brings up. Using protected procedures to handle interrupts.
Interrupts, like hardware signals, keyboard presses, sensor data, that kind of thing.
Precisely. Things that need an immediate reaction. A protected procedure can be directly linked to a hardware interrupt. But, and this is crucial, there's a rule about priorities.
Okay.
The priority of the interrupt itself can't be higher than the ceiling priority set for the protected procedure handling it. Imagine a super urgent interrupt. The handler needs a high enough priority ceiling so it doesn't get interrupted itself by something less important while it's working. It prevents delays for critical events.
Right. You don't want your emergency handler put on hold.
Exactly. The guide also flags a couple of things to avoid when you're defining entry barriers. Those are the conditions that control whether a task can even enter the protected object.
Okay. What shouldn't we do?
First, avoid using global variables in those barrier conditions. Globals can be changed by, anyone, anywhere, at any time, right?
Mm-hmm.
So your barrier could suddenly become true or false unexpectedly, messing up the logic. Second, avoid barrier expressions that actually change things that have side effects.
Why that bad?
Because it creates these hidden dependencies. Something happening in the barrier check could affect something else way over there, and it becomes incredibly hard to figure out why your program is behaving strangely.
Okay, so keep barriers simple and self-contained. The guide mentions a bounded buffer package example. Can you walk us through that, make it a bit more concrete?
Sure. So imagine a pipe or a conveyor belt with a limited capacity that's the bounded buffer. It's a protected type. It offers two main operations defined as entries: get, to take an item out, and put, to add an item.
Like queue.
Exactly, a synchronized queue. The key is the barriers. The get entry has a condition when count 0. You can only get something if the buffer isn't empty.
Makes sense.
And the put entry has when count maximum buffer size. You can only put something in if the buffer isn't full. Inside the protected object's body, you have the actual buffer storage, like an array, index pointers, and the item count. The protected object guarantees that these operations happen safely, even if lots of tasks are trying to get and put at the same time.
So it's basically managing the queue automatically, preventing errors like pulling from empty or adding to full.
Precisely. And the guide stresses that this is meant to be a lightweight way to handle this kind of data synchronization. You don't need the full overhead of a separate task just to manage a shared queue like this.
Ah, okay. So tasks are for bigger things.
Generally, yes. Tasks introduce a whole new thread of control. Protected objects are more about coordinating access within existing threads. They're more efficient for just pure data sharing and synchronization. Oh, and another point, protected types are inherently limited types in Ada.
Limited types. Meaning?
It means you can't just freely copy them around. This gives you very tight control, which is often exactly what you want for shared resources. You can use them to implement limited private types in package specifications, hiding the implementation details even more securely.
Okay. You mentioned earlier the protected procedures are good for interrupt handlers. What makes them a good fit, specifically?
Well, a few things. They're designed for short, quick execution, just like interrupt handlers need to be, right? They shouldn't block.
Right. Get in, do the job, get out.
Exactly. They also fit neatly into Ada's priority system, which is crucial for real-time stuff. And because the core operation inside is protected, non-interrupt code can safely interact with the data it manages without complex locking. The barrier mechanism is useful too. An interrupt handler could change some state in the protected object, making a barrier true, which then lets a waiting normal task proceed.
Like flipping a switch for another task.
Kind of, yeah. It's a clean way to signal from an interrupt level to a task level.
And the warnings about globals and side effects and barriers, it all comes down to predictability, doesn't it?
Absolutely. You need to be able to reason about when a task can enter and when it can't. Globals and side effects just throw a wrench in the works, making behavior unpredictable and debugging a nightmare.
Okay. But the guy does mention one case where you might need to put the protected object itself right in the package interface, not hidden away. When's that?
That's usually when a client, the code using your package needs to use an Ada select statement with an entry call on that protected object.
The select statement.
Yeah, it allows for things like timed entry calls. Try calling this entry, but only wait for, say, 10 milliseconds. Or conditional entry calls, only make the call if you can get in immediately. To do those kinds of calls, the client code needs direct access to the entry.
Ah, okay. So for those more advanced calling patterns.
Exactly. But generally, you'd keep it hidden inside the package body.
Okay, so protected objects are our main tool for safe data sharing. When do we bring in the heavy hitters, the tasks?
Tasks are for modeling the actual independent, concurrent activities in your system. Think of them as separate flows of execution, conceptually running in parallel. They let you structure your program around these concurrent parts, like different agents doing their own thing.
And they communicate using rendezvous. Sounds formal.
Yeah. It's basically a synchronized meeting. One task, the caller, makes an entry call on another task, the server. The server has to explicitly accept that call. While the accept block is running, the two tasks are synchronized. The caller waits until the server finishes the accept. They can exchange data during this time. It's synchronous and unbuffered.
So the caller is blocked until the server's done with that specific interaction.
That's right. It's a tight coupling for that moment.
The guide uses a stock exchange simulation to show this. What's the takeaway there?
Yeah, that's a great example. It shows how you map the naturally concurrent things to tasks. So the ticker tape showing prices, that's a task, it's always running. The specialist matching trades, task. And investor placing orders, task.
Okay, the active parts are tasks.
Right. But then look at the shared resources they use. The display where the ticker tape writes or the transaction queue holding orders. Those are implemented as protected objects.
Ah, I see the pattern. Actors are tasks. Shared resources are protected objects.
Exactly. That's a key design principle the guide highlights. Use tasks for the active entities. Use protected objects to manage the shared data they need to access safely. Tasks give you that model of separate little programs running concurrently.
So even though tasks can communicate directly via rendezvous, the guide seems to lean towards using protected objects for most synchronization anyway. Why is that?
Generally, yeah. Protected objects are often more flexible and can lead to fewer bottlenecks. A rendezvous always involves two active tasks coordinating, which can sometimes be less efficient than just having tasks interact with a passive protected object holding the data.
Less waiting around.
Potentially, yes. The guide even suggests that if you have a task that mostly just sits there acting like a mailbox or a buffer, maybe it should have been a protected object in the first place. It's often a more efficient pattern for managing shared state. Remember, anytime tasks share something that requires multiple steps to update, you probably need synchronization, and protected objects are often the smoother way to do it.
Okay, tasks for actions, protected objects for data. Got it. Next up, discriminants. What are these?
Discriminants are kind of like parameters you can give to a type when you declare an object of that type. For
Hmm.
protected types and task types, they're a way to customize or configure the object right at the point of creation, often avoiding the need for a separate initialization step.
So setting things up immediately rather than creating it and then calling an init
Ex-
function.
Exactly. For a protected object, you could use a discriminant to set, say, the size of an internal buffer or maybe the size of an entry family.
Entry fan.
Yeah, like an array of entries. You could also use a discriminant to set its priority or even tell it which hardware interrupt it's supposed to handle.
Okay. And for tasks.
Even more useful, arguably. You can use discriminants to set a task's priority, its stack size, the size of its entry families, and this is a neat one, associate data with the task using something called an access discriminant.
Access discriminant. Sounds like passing a pointer.
Essentially, yes. In ADA terms, an access value. The guide has a worker task example. This task type takes an access discriminant pointing to some task data. When you declare a worker task, you pass in a pointer to the specific data that worker needs.
And that data is then just linked to that specific task instance.
Right, it's bound to it securely. The guide contrasts this with the older way, which often involved an initial rendezvous you'd create the task, then immediately call an init entry to pass in the data. Using discriminants is usually simpler and less prone to errors.
Just cleaner setup.
Yeah. It's a lower overhead way to specialize protected objects or parameterized tasks right from the start. And the security aspect of access discriminants is good too. The link is constant, it can't be accidentally detached.
Any downsides?
Well, one thing to watch out for with access discriminants, the data being pointed to could still change after the task starts, potentially by some other part of the program. You need to be aware of that. Sometimes the task might need to make its own copy if it needs a stable snapshot.
Okay. Moving on. Anonymous types. The guide talks about single task declarations, like task T.
Right. The guideline is, if you know you're only ever going to need one instance of a particular task or protected object, consider declaring it directly like that, rather than defining a task type T-type, and then declaring T-type.
Why? What's the benefit?
It just makes it clearer in the code that this is intended as a singleton. It avoids creating named types that are only ever used once, which can clutter up the namespace.
And if you change your mind later and need more?
The syntax change to create a name type is trivial. The guide does warn, though, that while changing the code is easy, redesigning the logic of your program to handle multiple instances might be more involved. But starting anonymous is often a good default for unique components.
Okay, signals intent clearly. Now, dynamic tasks, creating tasks on the fly.
The advice here is generally minimize it. Task startup often involves significant overhead, setting up stacks, registering with the scheduler, and so on.
So it can be slow.
It can be, depending on the system. The recommendation is often to create a pool of tasks up front and reuse them, maybe having them wait on an entry for new work, rather than constantly creating and destroying them.
The guide has a discouraged radar track example. What goes wrong there?
Ah, that example shows the danger of losing track of dynamically created tasks. If you create tasks in a loop, say, and only keep a variable pointing to the latest one, the older ones might still be running, consuming resources, but you've lost the variable that let you refer to them.
So they become like ghost tasks. You can't talk to them or tell them to stop.
Exactly. It's a potential resource leak, and you can't signal them or abort them cleanly. It's like launching boats without tying them to the dock. They just drift away.
Are there any good reasons to use dynamic tasks then?
Sure, if the number of tasks you need genuinely varies a lot during runtime, or if you need very specific control over the order in which tasks become active, dynamic allocation might be necessary. Ada doesn't guarantee activation order for statically declared tasks, but the overall message is use dynamic tasks cautiously and manage them carefully, much like you'd manage any dynamically allocated memory.
Right, the usual heap management headaches apply. Okay, next big topic, priorities. This always sounds like it could get complicated.
It certainly can. First warning from the guide. Don't rely too heavily on Pragma priority unless you know your Ada environment fully supports the real-time annex and priority scheduling. Behavior can vary otherwise.
Good caveat. And what about priority inversion? That sounds bad.
It is. That's when a high priority task gets stuck waiting for something locked by a lower priority task, potentially because a medium priority task is keeping the low priority one from running and releasing the lock.
Ugh, sounds like a traffic jam caused by someone cutting in line way back.
Kind of. The guide recommends using protected objects with ceiling priorities to minimize this risk. Ceiling priority basically bumps up the priority of the lock temporarily, preventing those medium priority tasks from interfering and allowing the low priority task to finish its critical section faster.
Okay, but the guide also says not to use priorities to guarantee execution order. Why not? If task A has higher priority than task B, shouldn't A always run first?
Not necessarily, especially when they're interacting. The guide gives an example. Tasks T1, high priority, and T2, low priority, both call an entry on a server task. If T2 calls first, its request usually goes into the server's entry queue first. By default, entry queues are FIFO first in, first out.
Not priority-based.
Not by default, no. So the server might accept T2's call before T1's, even though T1 has higher priority. It depends on arrival order at the server's queue, not the caller's priority, unless you use special queuing policies from Annex D. Trying to force order just using priorities is fragile and can lead to subtle race conditions. Different ADA systems might schedule or queue things differently too.
So relying on it makes your code non-portable and potentially buggy.
Exactly. Use priorities for importance and responsiveness, but use proper synchronization mechanisms, like protected objects or rendezvous, for ensuring correctness and order.
The guide mentions the priority ceiling protocol again here.
Yeah, that's a more formal mechanism built into ADA with the real-time annex, specifically designed to bound priority inversion and prevent certain deadlocks related to resource locking.
And one last point on priorities. Sometimes the most critical task doesn't need the highest priority.
That's right. Think about a system with lots of tasks. You might have a very important calculation, but it only needs to run occasionally. You might also have a less critical task, say reading sensor data, but it must run every 10 milliseconds without fail. That sensor task might need a higher priority to guarantee it gets its frequent time slot, even if the big calculation is arguably more important overall.
Okay, priorities are nuanced. Let's talk about delay statements. Seems simple. Just pause, right?
Well, yes and no. The guide's main point is, don't expect delay 5.0 to pause for exactly 5.0 seconds.
Oh.
It guarantees a delay of at least 5.0 seconds. When the task actually wakes up depends on the system clock resolution, other tasks running, scheduler decisions. It's a minimum, not an exact duration.
So we need periodic actions? Just using delay can cause drift over time?
Precisely. If your delay is slightly longer each time, your task's timing will slowly drift later and later. That's why the guide recommends delay until for periodic behavior. You calculate the next specific time you want to wake up and delay until aims for that absolute time. It automatically compensates for previous variations.
That makes sense. Keep it anchored to the clock.
Exactly. The periodic task example shows the drift problem with relative delay, and pull device shows the delay until solution. And please avoid busy waiting.
Just looping and checking a flag.
Yeah. Loop exit when flag, end loop that just burns CPU cycles, potentially starving the very task that's supposed to set the flag. If a task needs to wait, use a proper blocking mechanism. Except select an entry call or a delay statement. Let the scheduler put the task to sleep so others can run.
Got it. No spinning. Any other quirks with delays?
Just be aware that the delay duration might be rounded up to the system's clock tick granularity. Annex D helps by guaranteeing ticks are no more than a millisecond, but it's still not infinitely precise.
Okay. Let's shift gears to extensibility. How does concurrency play with things like inheritance and making code reusable? The guide mentions generics.
Right. This is about designing concurrent components so they're easy to adapt or build upon. The guide advises being cautious about embedding protected types deep inside tag type inheritance hierarchies.
Why is that?
If you put a protected component in a base class, you might lock down the concurrency model too early. Derived classes might want different or more complex concurrent behavior, but they're stuck with the mechanism inherited from the base. It can limit how you extend the concurrent aspects later.
So maybe add the protection lower down in the hierarchy.
Often, yes. Keep the core data structures more general and add the specific protected object wrappers at the level where you need that specific synchronization. It keeps the base types more reusable.
And generics, how do they help?
Generics are great for creating reusable concurrent patterns. Say you need a thread-safe queue or a synchronized counter. You can write a generic package or protected type that implements the logic, parameterized by the type of data it holds. Then you instantiate it for integers, for strings, for whatever you need. You reuse the concurrency logic without rewriting it.
Template for thread safety.
Pretty much.
Okay, let's dive into communication details. Efficiency first. How do we make task communication snappy?
Key advice. Keep the work done during a rendezvous. Inside the accept statement, absolutely minimal.
Why minimal?
Because remember, the calling task is blocked for that entire duration. If the server task does a whole bunch of complex calculations inside the accept, the caller is just stuck waiting.
Ah, right, holding everyone up.
Exactly. Do only what's essential for the synchronization itself, maybe exchange parameters, update a critical status flag. Any heavy lifting should ideally happen after the accept statement completes so the caller is released sooner. The same applies to work done inside a selective accept loop. Keep it brief so the task can get back to checking for other incoming calls.
And again, the guide points to protected objects as often being more efficient for simple data exchange.
Yes, because protected object calls usually involve less overhead than a full task context switch and rendezvous setup. If the operations are short and non-blocking, they're typically faster.
Makes sense. Now, robustness, defensive communication. How do we stop tasks from crashing each other?
Exception handling is key. The guide highlights program error. This can happen if a task hits a select statement where all the guards are false and there's no else part. The task gets stuck. You should have a handler for program error in tasks with such selects. Always be ready for tasking error. This pops up in the calling task. If something goes wrong with the task it's trying to call, maybe the target task terminated unexpectedly or got aborted. You can't always prevent it, so you need to handle it gracefully.
Just catch it and decide what to do.
Pretty much. Don't let it kill your calling task unexpectedly. Also, consider handlers inside the accept statement. If an error happens while the server is processing the rendezvous, what should happen? Maybe log the error, maybe re-raise it for the caller to deal with. When others handler there can be a good safety net.
Okay, handle your errors. Now, those task attributes, count, callable, terminated, the guide seems wary of them.
Extremely wary because of race conditions. Think about it.
Yeah.
You check callable is the task ready to accept a call. It says true. But in the tiny fraction of a second between your check and you actually making the call, the target task could terminate or abort. Boom, tasking error, even though you checked.
So the information is potentially stale the moment you get it.
Exactly. Callable and terminated are reliable once they become false and true respectively, but you can't rely on them being true now to guarantee success next. And count the number of tasks waiting on an entry is even less reliable for tasks because callers can disappear from the queue due to timeouts or aborts.
Is count better for protected objects?
Yes, the guide notes it's more reliable for protected entries because modifications to the queue are themselves atomic operations within the protected object. But still, use with caution, don't base critical logic solely on count.
Okay. And the guide is really strong on avoiding unprotected shared variables for communication.
Absolutely. Just don't do it. It's the classic recipe for race conditions and corrupted data. If task A reads a value, task B modifies it, and then task A writes a new value based on the old one it read. Chaos. There's no locking, no synchronization.
Use protected objects or rendezvous instead.
Yes, use protected subprograms or entries. They provide the necessary mutual exclusion. If you absolutely must use a shared variable, like for memory-mapped hardware, use pragma volatile or pragma atomic to tell the compiler this variable can change unexpectedly and potentially enforce indivisible access, but it's still risky territory compared to proper Ada concurrency features. Also, avoid using non-local variables in entry guards for similar reasons.
Got it. What about conditional and timed calls or selects with else or delay? Any pitfalls there?
They can be tricky. Conditional calls, select else, or timed calls introduce timing dependencies. How quickly is the condition checked? How accurate is the delay? It can vary between implementations. You can even accidentally create busy wait loops if you're not careful.
Like constantly checking an entry in a loop with a tiny delay.
Yeah, or using an else part in a loop without a blocking call somewhere. Again, the guide often suggests that if you find yourself needing complex, timed, or conditional logic around data access, maybe a protected object could provide a cleaner, safer solution. And generally, try to keep the number of accept and select statements per task manageable. Simpler control flow is easier to reason about.
Okay, last major section, termination. Getting tasks to stop cleanly.
Right? First point, don't let them terminate unintentionally. Use exception handlers inside the task's main loop, especially around rendezvous calls. If a call fails with tasking error, maybe the task can log it and try again, or switch to a different mode rather than just dying. The recognize degraded mode example shows this.
And don't create tasks that never finish.
Unless that's explicitly what you want, no, because the main program usually waits for all its child tasks to terminate before it exits. An infinite loop task can hang the whole program.
How do you shut down tasks cleanly then?
If they depend on library packages, make sure they finish before the library cleanup happens. Often you'll design tasks with a specific shutdown or exit entry that the main program can call. And definitely don't use ada.uncheck deallocation on a task that might still be running.
Bad idea.
Very bad idea. Also, consider using a terminate alternative in your select statements.
How does that help?
If a task is only waiting on accept statements and all the tasks that could call it have already terminated, the task could be stuck forever. A select with a terminate alternative allows the task to gracefully exit if it becomes clear that no more calls are possible. It's a way to avoid deadlocks on termination.
So, include terminate if there's no else or delay.
Generally good practice, yes.
Ow.
And avoid creating tasks inside finalized procedures. That's usually too late in the shutdown sequence.
What about the abort statement? The guide seems very against it.
Strongly against it. Abort is brutal. It stops the target task dead wherever it is without any cleanup. It can leave shared data in a completely inconsistent state. It's almost impossible to reason about the state of the system after an abort.
Any alternatives if you really need to stop something?
The guide suggests looking at the asynchronous select statement, select then abort. It's complex, but it offers a slightly more controlled way to interrupt a task's execution during specific operations, allowing some cleanup, potentially. But even that should be used sparingly, and definitely don't modify non-atomic global variables from an abortable part.
So, abort is basically a weapon of last resort. Maybe not even then.
Pretty much. Far better to design tasks with clean exit paths.
And finally, put an others exception handler at the very end of every task body.
Yes, it's your safety net. If any unexpected exception propagates all the way out, this handler catches it. The task can then, at minimum, report that it's dying and why, log the exception, instead of just vanishing silently, which makes debugging much harder. The track task example shows this reporting.
Anything else on termination?
Just the usual warnings. Avoid circular task dependencies that lead to deadlock. Task A calls B, B calls A. And if multiple tasks might set the program's exit status, make sure you synchronize that access to avoid race conditions.
Wow. Okay, that was incredibly comprehensive. A real deep dive into the Ada concurrency guidelines.
It covers a lot of ground.
It really does.
Yeah.
It's clear that writing solid concurrent code needs a lot of careful thought. Choosing the right tools, protected objects versus tasks, managing how they talk, handling errors, thinking about priorities and timing, and crucially, how they all start and stop cleanly.
Absolutely. The big themes are definitely use protected objects for safe and efficient shared data. Understand the trade-offs between rendezvous and protected objects for communication. Be super careful with priorities and delays. Don't rely on them for correctness alone. And have a clear plan for task life cycles, especially termination. It's all about building concurrent systems you can actually rely on.
And it makes you think, even though this is Ada specific, these core ideas, managing shared state, handling independent actions, dealing with timing and interaction, they must have parallels everywhere concurrency pops up, right? Other languages, maybe even just complex projects in general.
I think so. The fundamental challenges of coordinating parallel activities are universal. The way Ada approaches it with tasks and protected objects provides a really interesting structured perspective on tackling those challenges.
Something to chew on, those trade-offs between keeping things simple versus making things run in parallel. Where do those apply in your world?
Thanks for joining us for this deep dive.